Hello everyone, this is the experiment passage through magnetic flux gate. So we're going to start the Earth magnetic field using this setup. This is called the magnetic flux gate. It's also known as the Earth inductor. So there are coils around this circle, and there are around, so we can read the dimension here, there are 1,000 turns. And the inner diameter of this circle is 213 millimeter. So we have the Earth magnetic field around us. When the gate is placed like this, and the vertical component of the Earth magnetic field passes through this gate, and we will flip this coil so that there will be a change of flux due to the Earth magnetic field. And then there will be induced current in this circuit. And this gate is connected with the amplifier. So we can measure the induced current and convert it to induced voltage. That's really connected to the Logger Pro. And this is the software we're going to use. And the y-axis is the potential, x-axis is the time. So we can measure the impulse. There are three parts for this experiment. The first part is to measure the Earth magnetic field, horizontal and vertical component. The second part, I'm going to measure the strain, the magnetic dipole moment of this magnet using two different methods. First, I'm going to study the vertical component of the magnetic field. So we know the Earth magnetic field, horizontal, I have a compass needle here, so north-south, the horizontal component is along this direction. So the actual Earth magnetic field is like this, pointed downward. And horizontally, this is the horizontal component. And now I have a inductor coil like this. I have the vertical component pass through the coil like this. So this part, I'm going to study the vertical component of the Earth magnetic field. So I have a Logger Pro connected, and I have the profile ready to set. I'm going to pull this screw here so that the coil, I will pull here, the coil will flip, so that the total change of the magnetic flux will be 2 times the vertical component multiply the area of the circle. Let me click collect. Oh, actually I should first do the 0. It's already 0, but I want to show you how to do that. Click experiment. 0. So because there is no change of flux now, and there is no induced voltage. Next, I'm going to click collect. This is the data I got. So by flipping the coil, there is a change of magnetic flux, and this induces voltage here. And the maximum voltage is about maybe 14 millivolt. I want to find the impulse. The impulse will be the area under this voltage versus time graphs. So I highlight this section, click integral. This tells me the impulse, VIMP, we are using in this experiment. So now it's 2.969 millivolt second. So when you do the calculation, you will do 2.969 multiply 10 to negative 3 voltage a second. Next, I'm going to study the horizontal component of the Earth magnetic field. So this time, I'm going to locate my inductor so that it is parallel to the Earth magnetic field. And then I'm going to flip it like this, so that this time the magnetic field is the horizontal component of the Earth magnetic field that pass through the inductor. When I flip the coil, the induced voltage is caused by the horizontal component of the Earth's magnetic field. Very nice. So this time, the impulse caused by the horizontal component of the Earth's magnetic field is 0.9241 millivolt second. So the impulse for this one is 1.641 millivolt second. Next, I'm going to use the same device, the earth inductor, to find out the magnetic moment M of this bar magnet by using this equation in the manual. So I'm going to find out the impulse, and the D is diameter, that's given, and N is number of turns, that's also given 1000. I have a magnet, I'm going to into, out, into, out, into, out. I'm going to stop here. This is the one data I just collected, and this part I have a bar magnet stay at rest, and this part bar magnet stay at rest, and this part the magnet approach the coil, and at this point the bar magnet passes the surface, and this part is moved away from the coil. So the direction of the induced electrical potential is the opposite direction. Next, I'm going to calculate the impulse by doing the integral. So the insert part is the 0.25 for the moving away the 0.291. Theoretically, if the motion is a constant speed, the same velocity, if the motion is symmetric, these two areas should be the same. But apparently I did two different velocities. You see the integral is different. The last part of this experiment is using another method to find out the magnetic dipole moment. So this time I'm going to put this bar magnet along the direction of the Earth's magnetic field, and but the opposite direction. So the Earth's magnetic field north point to that direction. I'm going to make this bar magnet opposite direction of the Earth's magnetic. So I'm going to leave it there. I have a compass needle here. So initially when it's very far away from the bar magnet, so this is only caused by the Earth's magnetic field. So next I'm going to move this compass needle closer and closer to the bar magnet. Let's see what happened to the needle. So it's very far, the field caused by the bar magnet is very weak, so no much effect. Then I make it closer. Look at the compass needle, it's rotating, right? So you want to find the position. If it's too close, it will be opposite direction, right? So it will be attracted. So you want to move it at the position the needle is perpendicular, halfway from there, perpendicular. This is about the position. So I'm going to measure the distance from the center of the bar magnet to the center of the compass needle. Okay. So it will give me the distance here is about 10.9 10.5 centimeter. By using this distance, and we can calculate it from the procedure, plug in that number into this equation, you can estimate the value of the magnetic moment.